how you send those two customer prefix into the P routers without mixing them up on the router in here. So the basic concept is, from the PE routers, if we can add a tag, a field on top of the customer's prefix, right, and unique tag for a unique customer, that's how I can keep customer prefix separated within the P routers, right? So this is what we call VPN v4 prefix. So what does it, how we can define VPN v4 prefix? When customer prefixes are coming into the P routers, from the ingress PE routers, what they will do, they will add an RD, route distinguisher, on top of each customer prefix. And on a single PE routers, each customer prefix will have separate RD, route distinguisher. So if we add a route distinguisher, say from customer A, their prefix is 10.0.0.0/8, adding route distinguisher XYZ. And the second customer prefix 10.0.0.0/8 and route distinguisher ABC. So then two prefixes are separated. Make sense? So from two different customers, even the same prefix, but after adding the RD, we'll have a unique prefix for each customer. Right? So this is how we'll add RD on top of the customer prefix, and that prefix will become a VPN v4 prefix. And that VPN v4 prefix we can send across to the infrastructure. Make sense? So this is how the customer prefix is going from these PE routers all the way to the other side PE routers. We call it egress PE routers, right? When the prefix goes to the egress PE routers, now the question comes, okay, on the egress PE router, how we can ensure this customer's particular prefix will go to, on the other side, to the corresponding or the correct VRF of that customer's. Did you get the point? When the prefix comes from this side to the other side, on the other side we need to make sure the customer prefix, the RD that we have added, right, that is only to use within the infrastructure, and when that prefix goes to the other side PE router, egress PE router, we need to make sure we need to send that prefix to the corresponding VRF on the other side where we have another side of the same customer. That is what done by RT, route target. So route target means from here on the PE router, we add RD to distinguish the prefix within the infrastructure, and then we added a string on the prefix, and that string will facilitate when the prefix will go to the other side VRF, they'll just pull that prefix using the RT, and that will go to the corresponding VRF on the other side. And this is how we can isolate customer prefix within the infrastructure, and the correct prefix can go to the correct VRF. So far what we have discussed: P routers, C routers, VRF, VPN v4 prefix, RD, RT. Make sense? So many things. Any questions so far? Okay. So after we are able to create those separate VRF and adding RD, we can send a unique customer prefix within the infrastructure. And then on the other side, when the prefixes are going, then using RT or route target, we can make sure each customer prefixes are going to the corresponding VRF on the other side of the infrastructure. And in between your infrastructures, all the routers are having their IBGP running on. And this IBGP requirement is not different than your normal IP routing requirement. In your infrastructure, the way you have your IBGP plan, just leave it as it is. For L3 VPN, no change is required. Only what you need to do, you need to make sure on all the P routers, you have activated the corresponding VPN v4 address family. Okay, so if I need to glue those concepts now together, this customer is sending a prefix which is 10.0.0.0 coming to this PE routers. How PE routers keeping that customer prefix unique? It has got a VRF, virtual routers inside. Second customers, same prefix, collecting on a separate VRF. Two VRF are separate, so prefixes are not mixed up. Then on the other side, when they send that prefix to the PE routers, how they make sure the prefixes are still unique, still not mixing up? He is adding RD. These PE routers are adding RD on each customer prefixes. When you have RDs, this VRF has got a separate RD, this VRF has got a separate RD. So when you add RD on top of the same prefix, that prefix becomes a unique prefix on the other side, right? And that will become VPN v4 prefix. That VPN v4 prefix are sent across all the other routers. Now, the very common question is, here, do I need to create separate VRF as well? Because you collected customer prefix on the PE router using a VRF. Should I create VRF on the P routers as well for each customers? No, we don't need to. Right? Why? Because that is how we cannot scale. If we have like 10,000 or 5,000, 2,000 routers in my infrastructure, and if I need to create VRF for each customers in all routers, I cannot scale, I cannot run a big network. Right? So that is why the concept is VRF you only create on the egress router, where the customer sites are connecting. But in the IP core, you should have a system in place so that without touching any configuration, still you can carry the unique prefix within the infrastructure. And that is why the concept of VPN v4 address came in. So this egress router is converting those customer prefix into a VPN v4 prefix. And if you have created a BGP table in the infrastructure to contain those VPN v4 prefix, that's it. Doesn't matter how many customers are coming. So you just created one VPN v4 table. All the customers are connecting on the edge. Will send those prefix into that VPN v4 table, and they will exchange it on the other side or carry it on the other side. That is how we are creating a virtual environment within the IP core network. And by having a virtual environment, and if you see, when the prefix has been forwarded across, all the routers along the path are not checking the source address of or the destination address of the packet. What they are checking, from which level the packet came and to which level I'll swap it. I'll explain that now. So this is what our virtualized environment for L3 VPN. Now what is the next step? If you see the L3 VPN infrastructure, so those PE routers are sitting in between customer and my infrastructure, and I will create VPN v4 prefix for all the customer using RD, right? And send it across. And apart from RD, I will add another string, another tag on those customer prefixes, so that by looking at the tag, I can create VPN membership anywhere in my infrastructure. So for example, when the customer prefixes are propagating across the network, now the question comes, okay, how I will manage the VPN membership if I have got 10, 20, 40 sites connected? How I will manage the VPN membership? In traditional VPN, how you used to manage the VPN membership? You need to create new VPN tunnel going to the central site, right? And that was a very difficult job in a big environment. In a central site, how many tunnel you manage? How many tunnel you need to maintain? So many. But in L3 VPN, when you have the RT configured, it becomes very, very easy. If any customer is connecting here or any customer is connecting here, if you want to become a member of that VPN, how you do that? Just import his RT here and export your RT. That's it. Just import and export RT. You can very easily change the VPN membership. That is what benefit of MPLS L3 VPN. Okay. So let's go by the slide now. So when we create separate VRF for each customer, and this is how this router can contain different customer prefix in different VRF. I have already explained those things. Now you'll see a little bit of configuration part of it, how we can configure those. On this router, when you will create the VRF, next question comes, okay, how I will make sure this particular customer will belong to that VRF. What you need to do, that interface, what connects the customer, you just put that interface into that particular VRF. When that interface goes to that particular VRF, whatever the prefix coming on that interface, all goes to that VRF, which VRF it belongs to. All right? Okay. Any questions so far? What we discussed? Now what we'll do, we'll relate that ingress router when the prefixes are coming, how those are linked with the label, MPLS label. Before we configured MPLS L3 VPN, what we discussed, we have already created a label infrastructure, right? On the label infrastructure, if I go back to the previous slide here, to send the traffic from here, when it comes to the ingress PE routers, to reach from these PE routers to all the other PE routers, we have already created our IGP infrastructure. On the IGP infrastructure, we have already advertised the loopback address of all those routers, right? So from this router to that router, if we need to reach that IGP path has got a label switch path already built. That's what we call LSP. So from PE router to that PE routers, when the packets are going, what this router is doing is just checking what is my incoming packet. Incoming packet is a open, unlabeled packet, right? On the PE routers, when from the customer packets are coming, that is what an unlabeled packet. Make sense? That is what an unlabeled packet. On unlabeled packet, what the P routers function, P router's job? P router's job is to see what is the destination of the packet. What is the destination of the packet on the PE routers? That's done on the global table. When it is done on the global table, it finds the destination of that packet on the IGP table. Then it will check, okay, for that destination network, from here to go to the other side, my next stop is this router. What is the level, outgoing level to reach to the destination? So when it finds the outgoing level to reach to the destination, then what it will do, he will add a label on top of it. So that's how the incoming label start from here. Then when that label packet goes this side, this router, what he will do, he will just check the incoming label. And for that incoming label, what is the outgoing label? He will find it from the level forwarding information base. Right? So on all the routers, when they are forwarding the packet, they are not checking the routing table at all. What they are checking on the level forwarding information base. What is the source or incoming level and what is the outgoing level. And that's how they are swapping the packet all the way to the egress router. When it going to the egress router, then what egress router is doing, they are sending that packet to the destination without the label. In fact, the label swapping operations, if you see the MPLS, there are 3 operations like label push, label pop, and label swap. What he is doing? He is doing label push, adding label. What those routers are doing, label swap. When it comes here, what he can see from this router is just 1 hop away. This router is 1 hop away. So what he will do, he will just pop the label from the packet, and that's how the native IP packet will be going on the other side, right? So now if I go to the L3 VPN concept, now we go to the L3 VPN concept. What it is doing, as we can see, each prefix coming to the ingress router, that is the prefix 4-byte IPv4 prefix, right? That 4-byte IPv4 prefix, each ingress router, what they will do, they will add an 8-byte RD on top of it. So 4-byte IPv4 prefix plus 8-byte RD, altogether 12-byte is our VPN v4 prefix. The size of the VPN v4 prefix is 12 byte. And then with that VPN v4 prefix, ingress router will add route target as well. And the route target is only 8 byte. And then we have 4 byte labels. So those three things, the ingress router is sending to the routers in the infrastructure as a BGP update message. When this message is going to the other side, you see there is a second level is added on top of it, right? Second level. So what is the purpose of second level in MPLS L3 VPN? So we have introduced a new concept here. Initially what we saw, when we have our LDP infrastructure, from source to destination, we have added only one level and swapped the level to send the packet across. Then afterward, when we created the VPN service, it means apart from the main level, which is pointing to here. Main level is pointing from here to there on the packet. And then on top of it, we are adding another level which is for L3 VPN. What that level is doing? This level, which is the second level. So normally, if we use MPLS L3 VPN, they send 2 levels. One level is my transport level, which is the outer level, used to forward packet from ingress P router to the egress P routers, right? That's the purpose of the transport level. And when it goes to the transport level, then what the second level is doing? Second level is making sure the packet is going to the corresponding VRF. The purpose of second level is to make sure the packet is going to the corresponding VRF. Okay, so that is how we can create MPLS L3 VPN. I think this slide is not very clear on the projector, but I'm not sure the resolution of this one. So if you see the screen capture here, on the screen capture you can see all the prefix sent from your BGP. They have got your route target and you have got your transport level. Okay. So that's the control plane stuff. So if you see, so far what we discussed, the purpose of LDP at this stage between VRF, P routers, other side VRF is to exchange those level information. When those level information are exchanged between those P routers and PE router, based on that, they create their forwarding table, right? So when the forwarding table is created, then my packet can go across. So if you see the whole function of L3 VPN, most of the job, most of the tasks are done on control plane. Most of the tasks are done on the control plane. So what control plane is doing? Control plane is creating an environment on MPLS L3 VPN to tell all those PE routers what is my ingress router and what is my egress router, how to reach from ingress router to the egress router, and then that information, how to reach from ingress to egress router, are done using transport level of MPLS L3 VPN. And then afterward, when the packet reach up to the egress PE router, then your VPN level actually telling the egress PE router which VRF it belongs to. Make sense? If you see that things in this diagram, it will be much more clear. Okay, let's see here. That's what the control plane stuff, putting it all together. Is it clear at the back slide? Okay. Say, now I have a site here, site 1. The IP address is 10.1.0.0/24. That comes from the C routers to the PE routers here. Right? When it comes to the PE router, on the PE router it goes to the VRF straightway. Right? When it goes to the VRF, on the VRF here, that prefix next stop is this, right? On the VRF, next stop is this. When he send the prefix from here to the other P router, you see what he's sending? He's sending VPN v4 prefix. This customer prefix with an RD here, that's what the VPN v4 prefix, right? That VPN v4 prefix, next stop is home. On this router, when he send that to the P routers, who is next stop? Definitely next stop is not this, right? That's the BGP concept, not MPLS concept. That's BGP idea. When BGP collect the prefix, he collect the prefix. What is his next stop here? Next stop is this router, right? Then from here, when the prefix comes here with RD and next stop, what is the next stop? This router loopback address. And here you see he is sending an RD message and the level 100. What level is this? That is the VPN level distributed by LDP. When this level comes from here to the next router and then R2 here, he'll look at the RT. If the RT import RT said, this is what the export RT he said, and this is what the import RT. If the import RT match, this prefix will go to that particular VRF. So that is what the control plane. When the control plane stuffs are done, now let's see the forwarding plane, how data are exchanged. So now this guy sending a packet which destination is 10.1.1.1. When the packet comes to this router, what this router will do, the PE router, he will add two levels in here, right? One is the transport level to reach up to this router. So outgoing transport level is 25, and inside there is another level which is the VPN level. VPN level tells from this packet, from this router, when it goes to the other side, which VRF it will belongs to. That will be done by the inside level, VPN level. So now you see the packet. From here, when the packet comes on this router, P2 router, what the P2 router will do? He will just do a level swap from 25. That's the incoming level. He will map that with the outgoing level. What is the outgoing level? So for example, 50. Did you see the level swapping happening? Those level swapping paths are done before. That's the LDP concept. LDP did it before. So he is doing level swapping. Incoming level 25, outgoing level 50. So this is how packet comes here. And did you see from source, from here, ingress P routers to the egress P routers, when the packets are going, only the transport level will be swapped here. But inner level, as it is, 100, 100. So this is how packet will go across the network. And when it goes to the egress router, this P routers, P1 will do the PHP, penultimate hop popping. He'll remove the outer label. So that packet goes on the P routers here. This P routers here with the transport label. Now, this router will decide which VRF this packet belongs to. Looking at the label, VPN label, and he put the packet into the corresponding VRF. And that's how it will send the packet across. So that is what the forwarding plane of MPLS L3 VPN. Any question about the data, how MPLS L3 VPN, they prepared the control plane and how they send the packet across. If I summarize this concept, in MPLS L3, how they are doing it, from the ingress P routers, PE router, they will add VPN label, and that VPN label will be exchanged to the other P router through BGP update. So every routers, they will have two label. One is the ingress label, and other one is the sorry, not ingress label. One is the VPN label, which is the transport label, and the other one is VPN label, and the other one is the transport label. And when they will send the packet across, they'll only swap the transport label, and they'll keep the VPN label as it is. When the packet reaches to the destination end, then destination end will send that packet to the corresponding VRF using the VPN label. So that's what the very basic understanding of MPLS L3 VPN. Now we will tell you some services that can be provided by MPLS L3 VPN. So for example, load sharing. I'll explain some services in here, how we can do using MPLS L3 VPN. Before I go into that detail, how many of you has got that understanding of that L3 VPN, how it works? Not clear? Okay, this concept need to be a bit clear. Otherwise, if we go to that services, how we can do or configure more services, a bit challenging. How many of you understand LDP so far? LDP, right? So what is the job of LDP? LDP's job is to create label or and allocate label on your IGP path. Simple as that, right? Whatever the path we have in IGP, just allocate label to those. So if you see our infrastructure, all those PE routers, do we have reachability on the loopback already? Yes, I was using OSPF, right? How the reachabilities are there? Using IP forwarding, regular IP forwarding and IGP, the reachabilities are there. To have the reachability in IGP and IP forwarding, that was we are trying to sort of decouple to reach from those. To reach those routers, we are decouple those IP logic using a label on top of it, right? So when we have the LDP infrastructure, it means to reach all those routers in my infrastructure, I don't need any IP routing. I only need the labels. These things so far clear, right? Now the question comes, when I know how to reach from one side of the network to the other side of the network by using label, that's what we call my transport level, right, in the L3 VPN case. What else we need to know after that? From the ingress P routers, right, ingress PE routers, when we send the packet across, say if we connect one customer to PE1, and other customer to PE2, how those two routers will know on which PE routers the other sides are connected? VRF is on the PE routers only. VRF is on the PE routers only, but on the P routers, there is no VRF. Right? On the P routers, only VPN v4. So my question is, from one PE routers, how the other PE router knows his side is connected here? RT, yes. So you have RT on the other P routers. When you have the RT is telling, when you said import RT, it means he knows he has got one side and that router has got another side, because RT will map that. Make sense? So that's how we know from PE to PE, how those sides are connected. Now the second question comes on top of it. All right. RT is the control plane stuff. RT is the control plane stuff. By having the control plane stuff, RT knows, our router knows on two different PE, we have sides connected. But when our packet goes, do we have RT on the packet? Do we have RT on the packet? So if we don't have RT on the packet, then when the packet coming from PE1 going to PE2 on the other side, how that router will determine which VRF it belongs to? Did you get my point? Huh? VPN level is for that. Did you see the difference? RT is the control plane stuff. RT in the control plane, that telling the other router which VRF the prefix belongs to. Right? That's done. Control plane is done. When the packet comes, packet doesn't have any RT. Packet only has got levels. Then when the packet goes to the other side, then how other side router knows which VRF it belongs to? That's why the VPN level is there. Make sense? And how the P router and P router, they exchange the VPN level? Yes, level swap. But when you have the RT map import on both sides, right? Then they send from this router, they send that, you see that RT? Here. Each BGP update is sending RT plus level together, right? Did you see RT plus level together? So when on the other side, P routers, when they use the import RT, label is also going there. So now they will make a link or make a table of that on the VRF, make a table of that prefix and the label. Right? So when the packet goes, so they already, two VRF already exchange the label. Right? So if you see the VRF context table, then you can see that prefix linked to that particular VPN level. So when the packet comes, packet has got that incoming level from the other side, and when it goes to the egress P routers, by looking at the label, the router knows which VRF that packet belongs to, and it will send it to the particular packet. Did you see the difference then in how we can create a link between RT and levels, and how the layer 3 or VPN level is making sure which RT the packet belongs to? All right. Let's see some services, L3 VPN service. Okay. Normally when we create L3 VPN, what we do? Do we use the same RD for all the customers? Did you get my question? My question is, if I have a network here, I have got a customer, HSBC Bank, right? I have got a customer, bank HSBC. So HSBC Bank, one site is connected on P1, other side is connected to P2. Normally what we do, we use same RD, because that is what the normal convention, same RD for one customer. All the site will use same RD, right? So if we have the same RD, if I have a drawing board, it would be much better to explain that. But anyway, look at the diagram here. That's what my MPLS backbone. Customer 1 CE, he's connected to PE11 and PE12. That's what we call multi-link customer. Right? So, and there is another customer here, I mean same customer, there is a same customer but another site on P2. What we want to do, since the central site, this central site has got more than one connection, how we will do load sharing among those two connections. Did you get that point? So, for that load sharing, there are two scenarios. We could have two scenarios. One scenario is that customer site can be connected to my network using a single routers, right? Single routers connected to two different PE. Second scenario is two different routers, two different PE, right? So in first scenario, how we do the load sharing, because since we have two connections, when this site will communicate with this site, we want to share the load among two different paths. How we can do that? Okay. That's what my customer side. In this router P11, I have got a VRF, which is IP VRF green for this customer, right? Then I have a RD and route target configured. This configuration is on this router for that customer. Make sense? Okay. Now, on this router, I have got same VRF green, RD, this, route target configured. So when I have configured this, on the other side, this side, same as VRF green. You see, VRF name are same. Because same customer, three different sites. RD, he has used separate RD, he has used separate RD, he has used separate RD. So, after that, when they exchange the route, this prefix, when it comes to him, how many prefix he will see in the BGP? Look at the diagram. This guy is using prefix 171.68.2.0, right? 171.68.2.0. When he advertised that prefix into that router here, same prefix, so same prefix will come on this router. Right? BGP will select how many paths by default? One path, right? Since BGP is selecting only one path, then if you want to send the traffic via both the path, can he send it? No, because BGP is selecting only one path. Make sense? How you can tell BGP to send the traffic across both the paths? That's what we need to enable maximum path in BGP. How many paths you want to install at the same time? Right? You need to be a bit careful here, because you see, if we have same RD 311 here, then this router will not be able to learn two paths. Look at the board. First, here two things. If you want to use two path, then you need to send two prefix into BGP, right? Two prefix into BGP. Your prefix is one prefix, but if you add RD, separate RD, then those router will send both the path in here, because using RD we can distinguish the prefix. So when it comes here, then if you enable maximum path eBGP 2, then he can forward the traffic into two different paths. Otherwise he cannot. So that's what the requirement. You need to have separate RD for two different PE. This PE RD has to be separate, and this PE RD has to be separate. If you send it, then it goes to the RR. Since we have got a router reflector here, router reflector, if he collect two prefix with two different RD, then only you can enable EBGP multipath, otherwise you cannot. All right, hub and spoke. What is hub and spoke? Normally, when you create a L3 VPN, enterprise policy is all the VPN will communicate, like from one side of my VPN, when they would like to communicate with the other side, they will go via the central side, like this. Here, if you see, that's what we have one side, that is what other side. And this is what our side 3. So when we communicate from this side to this side, normally in MPLS L3 VPN, from this side to that side, it will come directly here. Right? But our company policy is, or enterprise policy is, when the packet comes from here to here, it will come via the central side. That is what our company policy, it will come via the central side. How you can implement this hub and spoke VPN using MPLS L3 VPN features? Did you get the problem? Our requirement, our scenario is from side A to side B, when they communicate, they'll come via the central side. That's what we call hub and spoke VPN. So using the common sense, like, how we can do that? Any idea how we can do that? Say, for example, from here, if we want to send the traffic across, if it need to come via this path, how we can do that? Common sense is, if this side, central side, if central side is sending a default route to all those spoke side, if central side is sending the default route to the spoke side, so when this side want to communicate with this side, it will come to the default route first. Right? Then routing will be happening, from there it can go there. This is how we can do it easily. Otherwise, if he don't send the default route, if this guy is sending his individual route to him, then routing will be happening like this. Right? So the idea is, when we create the RT import and export, you see RT import and export, I'm sending route target export 1-on-1, right? I'm not importing 1-1 in here. If I import 1-1 in here, then this prefix will come straight here. Right? Traffic will come directly as well. So he's exporting his own route. See, he's exporting his own route, this route. When you export this one, 171.68.1.0 with RT this one, he's also exporting his prefix with RT this one. And if he did import RT of this one, if you use import RT 1-1, then both the prefix will come in here. Right? And what he's exporting, he's sending his own prefix with export RT 2.2. So those two sides, spoke sides, what they are doing, they're just doing route target import 2.2, which he is exporting, and he's getting those default route installed into his routing table. Only the default route. What if he did import RT, another import statement, import RT 1.1, then what will happen? Huh? If he did import RT 1.1, if this guy, site 1 or site A, spoke site A is doing import RT 1.1, what would happen? Then his prefix will go straight there, right? Not coming via this central side. So that's why you need to see the import statement carefully. He has done only route target import 2.2. Who is sending 2.2? Who is sending RT 2.2? Only the central side. Right? So that's how we can implement hub and spoke VPN using RT. Okay. This scenario, hub and spoke again. In hub and spoke, this scenario is, now we have got two sub-interface for each side, spoke side. Two sub-interface for each spoke side. If we have two sub-interface for each spoke side, then his prefix will come all the way here, right? When the prefix comes all the way here, what will be the origin AS? Origin AS is this AS number, right? Origin AS is this number. Come all the way here. So when it's coming inside here, then same AS number is getting back again. And that is what? AS loop. So to BGP use an algorithm, AS number algorithm called, if his own AS number is already in the AS path, then there will be loop, right? So that's why BGP will not accept it. But if you want to make the violation, right, what we do this command called AS override. AS override. When you did the AS override, then the same AS number from this side can be used on the other side. All right, so that's the scenario 2. Hub and spoke, that we did already. Okay, this option is option 3. That's option 2. Option 2, what we are doing here, we are creating two VRF. Two VRF, say for example here, we have got two sub-interface. That's what we call, one is VRF in. In the VRF in, we are importing his RT, since we have got two interface, and another VRF, like here, we are creating VRF out. So when we are getting prefix from him, getting into the VRF in, and that's what the RT import statement here. Yeah, option 2, RT import statement here. So this is how when the RT import, both the prefix, you see both the prefix RT import coming here, and then on this routers, both the prefixes are there. When he's sending via the other link on the second VRF, we are using export 2.2. So both the prefix are sending from here, and they are doing import 2.2, import 2.2. So if you see the data plane, how packets are forwarded, from this routers, our VPN level 35, going here, then getting routed in here, and from there, again, outbound level 40, new level added, going to here, right? That's how we can use hub and spoke by creating two VRF, VRF in and VRF out. Another option called half duplex VRF. So how it works? So for example, if a number of sites are connected to the same P routers, if the number of sites are connected to the same PE router, normal case, what it could do? On the single routers, all the sites are connected here. We can create a single VRF. If we can create a single VRF, then what happens? From site A to site B, when the routing will be happening, that will not go to the central site. Did you get that things done? I mean, the problem is, you see, in here, we have got one C routers connected to one P routers, that C connected to the other P routers, right? So we can send that traffic across via creating two different VRF in and VRF out. But this case is only one P routers we have, and on a single POP routers, a number of sites are connected. On a single P routers, a number of sites are connected. So normally all those things can be routed within a single P routers. It doesn't need to go to the other side P routers, right? But our requirement is hub and spoke. All the packet will go to the central side. From the central side, the routing will be happening. How we can implement that? That's what we call half duplex VRF. Half duplex VRF means in each VRF, what we created here are so this one, we just send, yeah, that's the configuration. In half duplex VRF, what we did, we just did the export statement. Did you see? Sorry, we just did the route target import statement in here. We created two VRF. One is import, one is export. So all the prefixes from the customers, all the prefixes are from the, on the customers are sending to the export. So on VRF down, we are sending the export statement, and when that prefix is sent from this VRF all the way on the other side, and this side we are using import statement. So what we are exporting on the down green down VRF export, we are importing here. And on the other side, we are getting another VRF out, and we are sending the RT export 2.2. And here we can do only import 2.2, and this side also we have got 2.2. So prefix, even though on the same P routers, send it all the way across on this side, getting routed and coming back here, then they can get it on the other side. So that's what we call half duplex VRF. In one VRF, we are just sending export, and other VRF, we are doing import. Okay. Extranet VPN. Extranet VPN is something just changing the VPN membership. Just changing the VPN membership. How you do it? Say, for example, here we have site 1, site 2, site 3. So normally this site 1 belongs to VPN A, belongs to VPN A site 2. Right? Normally those two belongs, and this is what? A separate VPN. That's what a separate VPN. If I want, or if you want this separate VPN, he want to be member of that VPN as well. You want to be member of that VPN as well. How we can do that? Whatever the VPN export statement he is doing, RT export statement he is doing, I'm just doing RT import, the same RT import on this routers or this VRF. When you do the same RT import, then his prefix is coming on the other side. There is one issue here. If you do that way, if this site has got more than one prefix, not only one prefix, more than one, then all the prefix will have same RT. All the prefix will have the same RT. Say two prefix, and if you use same RT import on this router, then both the prefix will be imported here. But our case, we just want only one prefix to be imported, not all. Right? How we can control that? If we use export map and import map, then that will be much easier, or it can be possible. Okay, internet. How we can provide internet service from VRF? There are a number of scenarios for that. It can be using VRF specific default route. By having a default route, we can enable internet service or separate PC interface. Let's see what we do with default route. In the default route, what we do, VRF specific default route. In here, on the VRF, we need to create a hole on the VRF and point that VRF into the global routing table. Because in my global routing table, I have got all the VPN routes, including the internet. Right? In the global table, I have got, sorry, no VPN, only the internet routes in the global table. So what we do, did you see in here, IPVRF A, that is the configuration in here. Route target 100:1, and this is what the keyword. I'm creating a default route, IP route VRF, which is the VRF context, default route, and then outgoing interface. What is the outgoing interface? Where is my gateway router? And then there is a global keyword, right? So in this router there is a default route added. In this router on the VRF context, a default route is added that is pointing to the gateway router and a global keyword. So that is what the whole has been created, right? And then what we need to do? We need to advertise our customer prefix into BGP statically, or whatever we have done in here, we have redistributed into the BGP. So what happened when internet traffic is coming in here? You see, internet traffic coming in here, that has been labeled with the next hop router. This one is coming on the other side, and then when the return traffic comes, again there will be a label swap. It will match with the label, and it goes to the other side. So that is what internet with a global keyword. These options are not very popular. Why this option is not very popular? Because if you do global keyword on the VRF, then the problem is you are leaking, or you are creating a hole from the internet, a security hole, right? So normally, personally, I don't prefer to create a hole on my VRF. So what's the second option? Second option is to have a separate sub-interface for internet and separate sub-interface for VPN. So from the customer side, we have, say for example, SE0/2, that is pointing to the internet, and SE0.1, that is pointing to the VPN, right? So when customer are browsing the internet, that is going via SE0/0, and you add on this router, you add a default route to the internet via SE0/2, and the VPN is going via this one. That is much better option, because in that case, when you create separate sub-interface for internet, through that sub-interface you are going to the internet, and that interface belongs to the VRF you are using for your private VPN communication. Yeah, you see, internet packet is going from the global table, and your VPN is going directly. Okay. Oops. What happened? Oh, yep. Okay. IPv6 VPN service, that's what we call 6BP. Normally, what we discuss about okay. Normally, what we discuss about VPN is, you see, your IP core network is LDP enable. So since it is LDP enable, we don't need to configure IPv6. We don't need to configure IPv6 on the IP core network because it's LDP enable. So if from customer side to the other customer side, if they want to communicate, we can use the label based label swapping on the infrastructure to send even IPv6 packet across, right? How you can do that? On the PE router, we need to create VPN using an extension called VRF definition. That's a new way of creating the VRF on the PE router. Before when we created VRF, how we did it? We just create IPVRF and VRF name, right? But in new technology, new way of doing it is you create VRF definition. You use the command called VRF definition and create the VRF. And you activate address family within the VRF. Address family IPv4, address family IPv6, right? So when you configure address family IPv4 and address family IPv6 within the VRF, that collects the prefix, right? Both IPv4 prefix and IPv6 prefix. And then from here, you have already activated VPN v4 prefix. Through that VPN v4 prefix, those IPv4 prefixes are going across. Then afterward, what you need to do, you need to just activate VPN v6 prefix here. When you have activated VPN v6 prefix, so all the P routers are carrying two address family, IPv4 address family, IPv6 address family, but that is VPN v6 address. But your LDP is swapping just label, that's it. So both VPN, v4 and v6 prefixes are going across on the other side, and what you do, based on your RT import and export, those prefixes are going into the corresponding VRF. So in your IP core network, you don't need to enable IPv6 dual stack. Just have IPv4, but having label, you still can exchange or still can send IPv6 packet. All right, so just quickly we'll see the best practice. So in best practice, if you see L3 VPN best practice, normally we suggest to use RR even for your VPN v4 prefix. Use RR if you need to scale it up in a big environment. So don't change your BGP configuration. Don't change your BGP peering policy. Keep it as it is. Activate VPN v4 even on the RR, route reflector. That's it. When you configure your RT and RD, normally what we see either AS number or IP address. You should use unique RT and RD. Don't use same RD. Don't use same RD across each customer or single customer. All the site, don't use the same RD. The best practice is for different site, you should have different RD. Okay. There is a big no for this one. When you create the VRF, don't use your customer name. You better use any numbers, meaningful numbers, circuit ID sometimes, or VLAN ID. You better use public IP address for your PC link if you can afford that. This is very important. When you create your L3 VPN customers, you better use or you better restrict in each VRF how many prefix you can send or your customer can send. Because if you don't have any restriction on the VRF, how many prefix a customer can send, then your customer can send unlimited prefix into your VRF, and that will be your scaling problem. For the faster convergence of your L3 VPN, in Cisco devices, you use the peak age convergence parameters, which is prefix independent convergence. And we also need to consider RT constraint. What is RT constraint? RT constraint is if on some of the PE router, if you don't have any customers connected, right, But in your normal VPN, V4 or normal LDP infrastructure, even though a customer is not connecting to any of the PE routers, or on a single or for a single customers on a single PE router, none of the sites are connected, but that site still carrying all the customer prefixes, VPN V4 prefixes, right? That is not good. So if you want to have a scalable, say in any of the PE routers, if a customer is not connecting, then why I will get that customer's VPN V4 prefix on that PE routers? So that is what we call RT constraint features. Slow BGP peer. So on the RR, route reflector, if any of the PE routers is responding slow, so they will just remove that PR from that peer group or from the RR. That's how it will ensure the faster convergence. I think these features are in iOS 15. I saw this is enabled by default, RT constraint. Slow peer is also enabled by default, I think, on iOS 15. That's it, the presentation that we had for L3 VPN. Any question about the best practice? If no question, as a summary, what I would tell, we have covered only L3 VPN part. We haven't covered LDP. So if you have clear understanding on LDP, that would have been much better to understand the L3 VPN. And as a best practice, try to follow those best practice, especially unique RT and unique RD. That will make your life very easy for future scaling, right? Yeah, and then other part, also restrict maximum prefix on the VRF. Also restrict maximum prefix on the VRF. Yep, so that's it. Any other question now on that one? If not, then we'll go for a break, tea break, and then there will be another session after the break. So thank you very much.